random sampling. So that's just simple enough. That means each of the sample units would be chosen equally randomly. They all have the same probability to be chosen, and each of them would be randomly selected. So we try to avoid any haphazard sampling or any bias or any judgmental sampling that we choose each of the sample scheme. If that's the case, each of the sample unit would be chosen randomly. Simple random sampling is the building block of more of the complex sampling scheme. So we learn this, and then we can combine later on. We can combine with some other sampling scheme to form the multi-stage sampling, trying to have a better estimate of the sample estimate. So simple random sampling, we can obtain the random number from a random table, or we can generate a random number from Excel. In most of the statistical textbook, on the very last page usually is attached with a random table. So we can randomly choose any digits from the random table. Okay, so let's look at this example. We have a hospital of 700 patients record. We want to conduct a simple random sample of 20 samples randomly chosen from the records of 700 patients. So 001, 002, 700, they are all labeled for each of the patients. So we can try to generate the random number from the random table. Let's take 3 digits from the table. Are randomly chosen. Let's take the first column. So first 3 digits, 104, 223, 241, etc. So we can take up to 20 of them. But if you look at some of the data or some of the random numbers, some of them are greater than 700. So to be easier, we take 30 random numbers. So ignore those greater than 700. Then we can find the non-overlapping patients, because we assume we are doing that with the without replacement. So we can randomly choose 20 of the samples from the patients. Okay. What is good about simple random sample? Let's continue with this slide. Under the simple random sampling, that we can say this is an unbiased estimator. Why is that? Let's look at the population's mean. The population mean mu can be estimated by the sample y bar mean, the sample mean of the simple random sample of size n. So looking back to the population, the expected value of yi is equals to mu. So let's say if I randomly choose a particular sample unit from the population, the expected value of it equals to the mean value. The variance of the population yi, a particular sample unit is chosen, would equal to sigma square. From the sample, we calculate the y bar by adding up all of the yi from the first up to n divided by the sample size. So this is equals to y bar. For that, we calculate, or we prove that expected y bar equals to, we add up each of the candidates. So expected value of the left-hand side equals to the expected value of 1 over n summation of expected value of yi. Expected value of yi, we can find it from the population, is mu. So that is mu, adding them n mu divided by n. So we find that expected y bar from a simple random sampling sample mean is equals to population mu. So we can say that the sample mean y bar is the best linear unbiased estimator based on the simple random sample of size n. Then having y bar one-point estimate is not good enough. We want to say how well this y bar could be compared to other estimator from different sampling scheme, right? So we want to look at the variance of the y bar obtained from simple random sampling. So the variance of the mean is defined by n minus n divided by n minus 1 multiplied to sigma square over n. So this is for the finite population case. Do you remember what's the variance of our sample mean if this is under infinite population case? In chapter 2, we mentioned about that, right? So all along, we learned about statistical theory. Under the infinite population case, the variance of the sample mean would equals to sigma squared over n. But under finite population, we need to multiply to a factor. This is a finite population factor. It's equals to n minus n divided by n minus 1. So that's the difference between the infinite populations and the finite population case, how we estimate or how we find the variance of our sample mean. In the text, we also have a proof of that. Okay, so this is formula 3.3. The proof of the formula 3.3 is shown on the text. Variance of y bar equals to variance of the sample yi, adding them up together and divided by n. So we said that in the previous slide, that saying that if we drew the sample unit without replacement, then the covariance between the yi and yj does not equal to 0. So this case, this guy does not equal to 0, and we try to find what this is. Covariance of yi, yj, and go through the steps, is actually equal to sigma square over n minus 1, a negative value, okay? So plug in here, and then we find that equals to sigma square over n multiplied to a finite population correction factor. Okay, the proof is not examinable, so you try to understand it if that's okay, if you're interested, okay? So what it says is here, we define the variance of our sample mean obtained from simple random sampling, and that's equals to sigma square over n multiplied to the finite population correction factor. But most of the time, the sigma square, the population sigma square, is not obtainable. We don't have the true value of the population variance. Then we can try to use our sample variance to estimate. And we know that the expected value of our sample variance is indeed equals to n divided by n minus 1 times sigma square. So we can replace that. We can estimate the sample variance equals to so we put n minus 1 divided by n multiplied to sy square, substitute into sigma square here. And then we can find the estimated variance of our sample mean was indeed equals to n minus n divided by n, sample variance sy square divided by the sample size. So that equals to 1 minus a fraction of our sample size with the population size multiplied to sy squared over n. Okay, so in other words, we obtained our sample mean from simple random sample. This is an unbiased estimator for the population mean. And then we find that with that y bar from the simple random sample, how well it is to be estimated to the mu. So we look at the variance of it. If we have the true sigma square from the population, then we can use formula 3.3. If we don't have sigma square, we don't know from the populations, we can estimate the variance of our sample mean by formula 3.5 which is 1 minus n over n, multiplied to the variance of our sample divided by n. Okay. So this is the table to summarize what's going on so far in the population and the sample. Population, we have mu, or we use a notation of capital Y bar. So this is the true value of mu, variance of the population, true values of the variance, sigma square equals to each of the square distance of the yi to the mean value, taking square divided by n. Okay, so this is the populations of size n. We have the mean and the variance. Then we obtain the sample from the simple random sample. We calculate the y bar. And then within our sample, we can also look at our sample variance. And that was calculated by yi minus y bar, taking the square, add them up together. Since this is from the sample, like we mentioned earlier, we need to divide by n minus 1. Okay, so we want to look for the variance of our sample mean. If sigma square is obtainable, then the variance of our sample mean would equal to sigma square over n multiplied to the final population correction factor. If we don't have sigma square, we can estimate our variance of our sample mean by 1 minus f, which is little n divided by capital N, and multiplied to our sample variance sy squared divided by n. Okay. I hope all this formula is not too complicated for you. So again, like I said, all of the proof, you can, if you're interested, you can go through that. Otherwise, it is not examinable. If you have any question, feel free to drop me an email and I can explain the proof for you. So very quickly, we look at an example from the population of n, given the value are 1, 2, 3, and 4. So we can find the population mean, adding up together, divided by 4. Population true mean is 2.5. We can calculate the population variance. So look at each of the guy, 1 to the average, take a square, 2 to the average, take a square, and then adding them up, divide by 4. So the true variance for the population is 1.25. Now we select a sample from that population. Let's say we select sample of size of 2. So the total number of possible sample would be 4 choose 2. So likely, if we choose all the sample from these finite populations, would be 6 possible samples. That could be 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4, right? So each of the sample means would become 1 and 2 average would be 1.5, 1, 3 average would be 2, etc., etc. Each of them would have the same probability of happening. So we would have 1.5 appearing once out of the 6 cases. So 1, 6, 1, 6, 2.5 appears twice, so 2, 6, etc. Okay, so from the populations, we see that each of the guy can appear at the same probability of a quarter. But in the sample mean, each of them would have a bit of the distribution of the y bar. Let's look at the expected y bar. 1.5 times the value, probability, etc. That's equal to 2.5, which is the same as the population mean. So we can find that with this sampling scheme, it is the unbiased estimator. And how to calculate the variance of y bar? We can calculate that using the formal formula that equals to 5 over 12, or since we learned the formula of 3.3, so we can substitute the variance of y bar equals to the finite population correction factor multiplied to the true variance of the population divided by n, which is the same, 5 out of 12.